Okay, in this section we're going to talk about elements and compounds. So they're two different things. And here's an example. We're taking a bunch of stuff together, we're cooking it up and making cotton candy, and we're going to figure out if we have elements or compounds in that scenario. So here we go. So we want to find out how elements and compounds are different. You probably heard of elements before, and they're listed on the periodic table. So let's see how they're the same, how they're different. So an element is the simplest form of matter. It has unique sets of properties. So it has unique things like boiling point and color and a melting point. A compound is when you have two or more of those elements off the periodic table chemically combined together in a fixed proportion, like water's an example. H2O, there's two hydrogens with one oxygen. That's a compound. And it's got a ratio of how they're going together. So two hydrogens, one oxygen. So if you have like water, you can break that down into its elements. You can break it into just hydrogen all by itself and oxygen all by itself. So compounds, the definition of compounds can be broken down into smaller, simpler substances using chemical means, but elements you can't do that too. They're always going to remain the same. So chemical change, this is a very important concept, so I need you guys to know this one. I usually put this on quizzes and tests. A chemical change is a change that produces matter with a different composition than the original matter. So it will have a different composition from when we started with it. So a chemical change is going to change that. And it's going to be done by a chemical reaction. So a chemical change is a chemical reaction. So if something will react with something else, then that's a chemical change. So here's an example. When you put table sugar, if you decide to do this, put this on a pan on the stove, heat it up really, really hot, you're going to see that the white sugar turns into this black substance. And what we've done is we've removed some elements and we have just the carbon left from the sugar. So sugar has a lot of carbon in it. So we removed the oxygen and hydrogen that was in there. And we just have the carbon, like you'll see C on the periodic table. That's what we just have C right here. So this is a chemical change because we really got rid of some of the elements. We separated the elements from each other, and now we've had a chemical change. And you can see a chemical change. A good hint for that is you see a color change from the original to the new thing. You see a color change, it's almost always a chemical change. So here's an example. We took the sugar and we heated it, and we had carbon in the pan, and we also made water that evaporated into the air. You can also take water, remember H2O, you can put electricity through the water, and it's going to make hydrogen gas and oxygen gas. So this is also another chemical change. So any compound you have, you can do a chemical change to it, and it will change it into its elements that it's made out of. So usually the properties of a compound, like the properties of sugar, is a lot different than the properties of water. So sugar at room temperature is a solid, and water at room temperature is a liquid. So those properties are very, very different. So when we put sodium and chlorine together, we form sodium chloride, and there's a change in composition and a change in its properties when you have the difference between sodium and sodium chloride. So chlorine is this greenish, yellowish gas, and we use it in pools in liquid form, but this is a gas form. And it's really good for killing bacteria and viruses. That's why we put it in there. So this is a really good thing to kill COVID with. So viruses can be killed by this chlorine if it's in contact with if the two things are in contact for long enough, it will break down the virus. So that's why we use it in our swimming pools. And sodium is this silvery metal right here. And you might have seen these yellowish kind of street lamps outside. They're changing a lot of our street lamps to this kind of sodium vapor. And so they use this metal in the light to make that color. So that's the way sodium all by itself looks. It's super reactive. But if you put the two together, sodium and chlorine, it turns into this white table salt. So this is salt we use in our food. So very different in properties after changing into sodium chloride. So how can we distinguish substance and mixtures? So if the composition of material is fixed, the material is a substance. If the composition of the material can vary, then the material is a mixture. Remember we talked about Kool-Aid, we could have really strong Kool-Aid or really weak Kool-Aid. So that is a mixture. And so the composition is varying. If I make strong Kool-Aid or weak Kool-Aid, I'm varying the composition, and so I have a mixture. So here's a flowchart. You'll see this a lot in chemistry books, and it helps you remember how we can categorize things. So everything is matter. We know that anything you can see or touch is matter, except for light. Light's energy. Matter, we can say, hey, does it have a definite composition? Then it's a substance. Does a substance have a definite composition? Homogeneous? Then it could either be an element or it could be a compound. So this could be the sodium and this could be the sodium chloride. So if we can chemically separate the compound into elements, we can do that. So compounds are made from elements. So examples, silver is an element, and this is a compound, this beautiful gemstone. But what if we have a mixture? Remember, they can vary, like the Kool-Aid can be strong or weak. That means variable. If we can separate it physically, and then we can get our elements or our compounds out of it. If it's all the same, like top to bottom, side to side, we call it a solution. If it's not the same looking, top to bottom, side to side in the container, then it's called heterogeneous. Like if we have the oil and water, or we have rocks and water, that would be heterogeneous. So homogeneous, stainless steel looks really good. You might have stainless steel appliances in your house, and it looks shiny, and it looks the same top to bottom, side to side. Granite is a cool rock in the Sierras, where I love to hike, and it has, you can see speckles, different colors, so this is heterogeneous. I think you get the idea, but let's try this one. This one is the solid right here. We want to know what's going on. If we heat it, we can get a gas come off of it, and we can get a black solid. All three things that we're talking about, this stuff right here, and the colorless gas and the black solid, are substances. But we want to know if they're elements or compounds. So we know that we can heat the solid, and it makes this colorless gas and a black solid. We know a compound can be broken down into simpler substances by chemical change, but an element cannot. And heating can cause a chemical change. So what do you think about that greenish solid? Do you think it's an element, or do you think it's a compound? So we need to know if it's elements or compounds. So when before we heated it, we had one substance. After we heated it, we had two substances. So because we had two substances afterwards, we know that the beginning thing was called a compound because it made two new things when we were done. So we use I talked about the periodic table a little bit. We're going to use symbols for all of the elements that we see on the periodic table because it just makes things easier and faster for chemists, because we like to write everything in shorthand because we don't want to write too much. So we're going to have everything as a symbol. Okay, so we're going to have each element. You don't have to memorize them. You'll get used to them, and you'll always have a periodic table to use throughout the class. But you'll get used to the symbols after a while, so you don't have to hunt and peck too much on the periodic table to find them. So we use symbols to represent elements, and we use formulas to represent compounds. So the chemical symbols are kind of like letters in the alphabet, and formulas are kind of like a word. So we put element symbols together to make a formula. So back in the day, we talked about alchemists who were getting started with chemistry, and they used these symbols. And then the chemist came along called Dalton, and he came up with these symbols. So it's changing over the years. But nowadays we use these symbols. Some of them seem weird, like why is silver Ag? It's because it comes from a Latin word from a long time ago, because these things were all found in the natural world a long time ago. So the Greeks and the Romans found these things and they gave them their name here. So since it's been used forever, we just continue using a symbol based on that Latin name, because these have been around forever and ever. So people know about gold forever. A long time ago, they called it aurum in Latin, way back in Rome. So we still use that symbol because people were used to these words. So some of these seem strange. Some of these words are strange because they're from another language, but we still honor those names. So let's see what you remember. So if we pass electricity through a substance that we get oxygen gas and sulfur, is this a compound, a mixture, element, or solution? What do you think? We talked about this with water, so maybe you remember. So the things that came off of that were elements, so the substance that we started with cannot be an element. Alright, next one. Which of these is a mixture? So this thing right here is a sugar. So what do you think? So air's a mixture. We're breathing in right now. When you take a deep breath, do that. Take a deep breath. You're breathing in a lot of nitrogen gas and oxygen gas, and also some other things in there, argon and a lot of different small amounts of other gases. So it's a mixture. Last question. Which symbol do you think is for potassium? There's a hint. It doesn't start with a P because it comes from a Latin word. So what do you think? There's K is a symbol for potassium. So we'll get used to all of these symbols during this class. Okay, I hope you learned a little bit about chemistry. I'll talk to you soon. Bye-bye.